Hello, today we're going to finish up Flexural design, especially utilizing what is available to us in the manual. Up until now, we've mostly been talking about the equations in the spec, but now let's flip back to the beginning and talk about the design tables that are available. So, if I go to my spec, I have part 3, which is labeled beam, should be a tab called beam. And it'll tell you what is all in there. And we're going to specifically start looking at table 3.1, which are values of CB. That's not what I wanted. Right? I'm just looking down the list. I have table 3-1, which are CB values. CB was something that I could use, is a factor that I can use to convert my not constant moment diagram. My beam is not subject to a constant moment. My moment diagram varies along the length, and I can use that CB value to divide my maximum moment and make it seem like I am using a constant moment along the length. It is conservative to assume that CB is equal to 1 and I not reduce my maximum moment that I designed for, but this is allowed. So that would be something that is in page 3-18. Right? It'll say right up here, CB value for 1. For my lateral torsional buckling, if I have a single point load, I can divide my maximum moment by 1.32 if I have some lateral bracing, if I have no lateral bracing, or 1.67 if I have lateral bracing at the center or at the load point. And then if I have two concentrated forces, I can divide my maximum moment by 1.14 or as much as 1.67 if I have bracing at the load points. And this just goes on, and it tells you what you can divide your maximum moment by, assuming you have lateral bracing at certain locations. Again, assuming a CB value of 1 and not reducing your maximum moment is the most conservative. And you are more than welcome to do that as you design your beams. Table 3-2. Table 3-2 is where I start to be able to select my shape, the beam shape that I want to use, using my plastic section modulus ZX. Now, this is, let's go to table 3-2. And note the assumptions. Do I have a yield stress of 50 KSI? If I'm using something that doesn't have a yield stress, if I'm using a steel that doesn't have that yield stress, then I can't use this table. It also assumes a CB value of 1. It'll say that right here. If you go back to page 3-9, it'll look slightly different. Again, this is the 14th edition, but it'll remind you that, okay, you can use this for FY of 50 KSI, and CB is taken as unity. Again, that factor that I can use to reduce my W, or to reduce my maximum moment. Let's take it as 1, and so you basically don't reduce it. Now, keep in mind these equations right here. This is directly from the spec. And basically, what you are given in, I'm going to write this down, but what you are given in this table is your phi bending MP and phi bending MR. Phi bending MP is your maximum plastic moment. Strength, you know, phi MN basically. And phi MR is your maximum inelastic moment. And what they want you to do is basically interpolate. And that's what this phi BF is for. Right? Notice this right here, phi BF. Okay, I want you to keep that in mind when we go back here. You have a CB value. You can choose a CB value. You have your plastic moment, your maximum plastic design strength, this phi BF, which is basically, instead of you having to interpolate because it's a straight line between your maximum inelastic moment and maximum plastic moment, it's a straight line. And you interpolate assuming your length is between LB and LP. I feel like I'm throwing out a bunch of symbols. So let me start back. Let me go back a couple of slides. Here we drew this lovely thing, this lovely chart that kind of reminds you of the one from buckling, from the compression. And we have your maximum plastic moment. That's as much as you can get. That's assuming your entire cross-section has yielded. That is the maximum strength that you are going to get out of a section, right? MR, this is in between, right? MP, there, that might be a little bit better. MP, that's your maximum plastic moment. MR is your maximum moment for inelastic lateral torsional buckling. And this is a chart with your nominal moment and the unbraced length of your beam. So what they did is they took this value and they have a length for it, LP, your maximum plastic moment, and the length that corresponds to, that unbraced length, and your maximum inelastic lateral, well, I guess minimum because it's at that end. But it's where residual stresses start to accumulate, yielding within the cross section. So you have some inelastic lateral torsional buckling, and the length associated with that. And it's a straight line between these 2 points, your LP and MP, and your LR and your MR. Okay? Keep that in mind so that when you go to your this equation right here, this is basically if your unbraced length, LB, is less than your length corresponding to your maximum plastic moment, LP, I don't want to share anything. No, thank you. Then you basically get to interpolate and that is what this equation is. We're going to go through an example, okay? But your nominal moment, you're basically going to interpolate if your LB is between LP and LR. Actually, I'm sorry, I misspoke. When your lateral brace length is less, when your unbraced length is less than LP, then your maximum flexural strength is your plastic moment, right? That's what we just said right here. If your LB is less than LP, then your maximum plastic moment is going to control. If you're between LP and LR, then you get to interpolate between these 2 points. Okay? That's what this says right here. When your LB, and we're going to write this down, but just reading it directly from the manual, that's what this says. And that's what these values are. This is basically your slope. This VBF is your slope for interpolating. Okay? It says that, I guess, on the next page, right? VBF, right? That's what your slope. If you're interpolating, that's what you would write. So the manual is like, we're going to interpolate it for you. So if I'm using table 3-2, I need to know my unbraced length, and if it's less than LP, then I can just use this value right here. If I am in between, I get to know the BF value. So we're going to write that down. Hold on. Where were we? Right here. Now remember, this is assuming Fy of 50 KSI. And a CB of 1. This table provides your maximum plastic moment, assuming bending about the major axis. These are W sections, so the x-axis. Your maximum moment when yielding first begins to occur, resulting in inelastic lateral torsional buckling. Let's see. If your unbraced length is less than or equal to the length associated with your maximum plastic moment, your moment capacity is your maximum plastic moment. If it's not, did I do that the right way? Hold on. LP is the smaller one. LP, if your unbraced length, LB, is in between the two values, one corresponding to your maximum plastic moment and one the length at which yielding begins to occur, then you get to interpolate. Right? So this would be assuming you go through, you do yielding first, you divide your phi-mn, or your moment that you need by, here, let's write that down. Right? If you're given an MU and your Fy is 50 KSI, my yielding equals phi B Fy Zx. And I can solve for it. Zx, go to this table 3-2, pick something, make sure that in terms of lateral torsional buckling, which is what this table is giving me, that I'm okay as well. That means it would satisfy yielding and lateral torsional buckling. Now the next one I want to talk about, I wonder if I should even, yeah, okay. The next one I want to talk about is table 3-10, which you guys are going to look at and say, what is this? It's not really a table. It's a giant plot broken up into multiple pages. These are plots of moment capacity, right? Let me make sure. Moment capacity versus unbraced length, right? Your phi mn versus your unbraced length, LB. Again, these have some assumptions. We're assuming 50 KSI and a CB of unity, a CB equal to 1. Okay. In these charts, there are there's keys, right? A solid line, We haven't even looked at one yet, but write this down. A solid line means that you're choosing the lightest section available. Right? It's always about weight. We want it the lightest, most economical. And a dashed line means that it has the capacity, but not the lightest section. We haven't even looked at it. You probably are like, what are you talking about? Write this down. Okay, I'm going to go back and look at my spec here. Right, that was all by ZX. I can do it by I. If I choose it by I, that would be because I know that I'm only elastic. And there's some other tables. How much load can certain W sections hold? Can I fast forward here? This is what I'm talking about, okay? Available moment versus unbraced length. I have unbraced length down here at the bottom. And available moment, MN. Okay, so it's not VMN. Let me make sure. Oh no, it is VMN. Oh, sorry. Forgot that was ASD. What I was like, why wouldn't they give you the fee? And these are basically kind of big, giant, drawn out plots of this picture, right? We have a flat part, that's my MP, and then this little curve. Well, it's a straight line and then a curve. That's what this is. Here's my flat part. Here's where I start to interpolate between my plastic moment and inelastic lateral torsional buckling. Starts to look super funky, right? But just know that it's the chart for all W shapes using an FY of 50 and a CB of 1. That's why there are a million lines on here. But it's all the same chart, that moment versus unbraced length, but it's for a bunch of different shapes. That's why there are all these different lines. And you see it tells you the W shape that it's referring to. And we're going to do an example in a second. You want to choose the solid line if you want to choose the lightest section. Starts to get super messy looking. Just keep calm, draw your little dot of where you are, and choose a section, okay? So we're going to do an example of that right here. I've got, let's say I'm designing a beam, and I just put one up here, right? I want to choose a W section. It has an FY of 50. I'm assuming a CB of 1. I need 544 kip feet of moment capacity. And I have an unbraced length of 18 feet. Okay. I should get up a straight edge here. Let's see, 544. Okay, there's my 544. Oh, look, it's even drawn it for me, right? 544. And, why did you just turn that? Don't do that. Okay. And 18 kips, right? Sorry, I'm putting my straight edge on my smart podium and it's not liking it, so I just won't do that, right? Here's my 544 kip feet. Note that this is in kip feet. Kip feet. Always remember your units. Let's see, unbraced length of 18. It's cut off at the bottom, but it's in foot. So I have my number 18, and I'm going to draw my little line. So that's my spot, right? Hold on. I'm not going to do that. Right? This is at LB equals 18 feet. Phi BMN equals 544 kip feet. Now I want to go up and to the right. To the next black line, solid line. Right? W24 by 84 is, I think, that what that says. On the way, I hit a W16 by 89. I also hit a W14 by 90. Right? I'm going this way. Okay, I first hit that 16 by 89. Then I hit this line, which was a 14 by 90. I hope you have your notes in front of you because this is not very great quality. And then I hit my first solid line, which is a W24 by 84. You notice it's deep, it's 24 inches deep, but it weighs the least amount. It's an 84 pounds per foot. So if I'm going to design it, that's what I'm going to choose. It's my most economical. Right? Now, if I wanted to, I could go back to the spec and verify that. So let's do that. Right? I mean, I can look here and I say, okay, at 18 feet, if I go all the way up to 18 feet, before I hit that solid line, say it's somewhere around there. A W24 by 84 at 18 feet. That's an L. BBMN is about, it looks like it's like 570-ish. Right? That's what That's what this says to me, this table. I could go back and look at my spec, right? Let's see. A W shape. I'm looking for a W24 by 84. right? I am on page 3-24 of my spec. Not my spec, of my manual. The spec is in further into the manual. Right? And I'm going to do this on a new page. So hold on. From table 3-2, I'm looking at page 3-24 in my manual. My length corresponding to my maximum plastic moment is 6.89 feet. My length corresponding to the initiation of an elastic lateral torsional buckling, LR, is 20.3. Well, they said my LB was 18 feet, so I'm going to have to do that interpolation thing. The equation if you're looking at page 3-10, and it has to be less than my maximum plastic moment. Okay? I'm going to give you guys a second to write that down. So I need to go back to page 3-24 and figure out, I'm going to do a CB of 1, right? That's what it said. So, all right. That doesn't matter. I need to find out my maximum plastic moment and this number that's used for interpolation. So back on page 3-24, my maximum plastic moment for a 24/84 is 840 kip feet. And then that phi b BF factor is 24.2 kips. I hope everybody sees where I'm getting that. I'm going to give you another minute. I'm on page 3-24. About halfway down the page. So if I want to calculate my maximum moment capacity, 1.0 times 840 kip feet minus 24.2 kips times, oopsies, I'm sorry, this is a B. I hope you guys figured that out. My unbraced length minus my length corresponding to my maximum plastic moment, LP, 6.89 feet. And let's calculate that. Should get a value of 571 kip feet. See, what they wanted to know was what's my lightest section to hold a 544 kip foot moment. I used the design tables. Like I say, it's called a table. It's more like a chart. To pick the lightest section, AW 24 by 84, because it had that solid line. And see, I guessed, I was like, it's about 570. Yeah, I thought it might be a little bit higher. And in fact, if we calculated it, it was 571 kip feet. So that is how we use this design chart. Okay. Yeah, we don't need that. I realized there was some artifacts in here from last time I taught this, which they were clearly a little behind, but that's okay. They had their compression exam right after this lecture. So let's do one example. And I will do the second example with you guys. Actually, I have, oh, there's some more stuff. Yeah. I have a bunch of examples. We can do the first one. Yeah. Okay, I'm going to quit for now. This is 40 minutes long already. And then I'm going to come back and do a design example. Okay?